Hello everyone. So in this lesson, I'm going to tell you about electromagnetic induction. This is going to be a little bit different in that for this one, normally if we were in the lab, I'd have a lot of demos set up. But for this one, unfortunately, because of where we're at, I'm going to have to link to a bunch of different videos. So I'm going to give you a bunch of different videos that demonstrate electromagnetic induction in a few different contexts. And every time I link to a video, I'm going to do something like that. That's the right corner. That might be that. I'm not quite sure. Anyway, maybe I'll just do that and hedge my bets. And there'll be a little thing that shows up, a little link that shows up in the corner, and that will take you to the video where you can see the demo happening. Because again, I can't really do it live because I'm basically in a closet. Okay, so check that out. Anyway, so quick recap is where we're at so far. First of all, we've been talking about how a little while now that current carrying conductors, so wires. Oh no, my wire. Okay, so we've been talking about for the last little while about how current carrying conductors, i.e. wires, can be used to create magnetic fields. Remember, thumb, current, fingers, magnetic field, right? Of course you do. Boom. So as long as we have a current flowing through the conductor, we're going to have a curling or whatever, coiling magnetic field. It's not coiling, but anyway, curling magnetic field. Okay, boom, just like that. And from last time, Ampere's law told us that we can actually use these things, use the current, if we know the current, to figure out if we're a certain distance away, right? If I have my ruler and I measure, okay, I'm 10 centimeters away from the current carrying conductor, I wonder how much the magnetic field is 10 centimeters away. Okay. The only problem is that if you're going to do it properly, you need to know something about integral calculus. So instead, what we did is basically said, okay, let's keep the geometry simple, and that way we can not have to know integral calculus. Not yet, anyway. Stay tuned for. I won't teach you that. Somebody else is going to. Anyway, so. Remember the days when we could actually go outside? Sure you do. And remember how there were these places called amusement parks where people would go and be entertained? Sure you do. Well, if you've ever been to one called Canada's Wonderland, it's near Toronto, they have a ride there called the Drop Zone. And the Drop Zone is actually one of my favorites. So I'm going to link to a video that shows the Drop Zone right here or here. Go watch the video.
2,000 years later.
Okay, wasn't that cool? Did you notice that as the cart came down from the top that it started slowing down, right? There were brakes. But unlike the brakes in your car, the brakes in the drop zone aren't mechanical, right? They're not like disc or drum brakes like you might have in a car. They're a completely different thing. For one thing, you probably didn't hear any sound. When the cart slowed down, it just kind of slowed down like magic. So what's up with that? Why are there no screeching brakes? I mean, that car has a huge mass, and it slowed down pretty quickly. You would think that there'd be like all kinds of terrible noises as the brakes engaged, but none of that happened. What's going on? So to explain it, I need to tell you a little bit about Faraday's law of electromagnetic induction, which is pretty complicated sounding, but don't worry, I know you can understand it. So the idea is that we've seen how if you have a current carrying conductor, that creates a magnetic field. Here's the cool thing. You can also turn it around, and if you have a magnetic field that changes in time, right? A magnetic field that is somehow changing its, well, I'll use the proper word, somehow changing its flux, then in that case, you can actually have a voltage created in your conductor. It's pretty wild. Okay, I'm going to link to another video, but as you watch this video, I really want you to pay attention to the ammeter, right? The little needle thingy that he has on the side. Okay, so check out this video, and while you're watching it, you only need to watch about the first minute or so. While you're watching it, watch what he does. And more importantly, watch the needle. See what it does, okay? So check out the video here or here.
One eternity later.
Wasn't that cool? I basically took a magnet and put it near the coil, and all of a sudden you had a current being registered, right? Or a voltage, I guess, depending. In In the video, he kept talking about a voltage, but I normally think about it in terms of a current. Anyway, wow, that's so cool. Like, what's going on there? All of a sudden, we have a magnet coming close to a conductor, and magically, it's not magic, it's physics. Come on, of course it is. Physics, because physics says so, we're going to have some kind of a current. Okay, so I don't know if you noticed, but what kind of variables or what kind of things can we change in order to change the induced current? Any ideas? Try and think of some. All right. Now I need to tell you about one more thing. If Faraday's law of electromagnetic induction is like the present that you receive at your birthday, Lenz's law is the bow on top. It's what makes everything so cool. So check this out. So you have your coil, and you move that magnet close to the coil, and all of a sudden you get an electric current or a voltage or whatever. I'm just going to say current, okay, just to make it simple. So you've got your magnet, and you move it close, and you get a current. But remember back to Ørsted. Ørsted says that as soon as you have a current carrying conductor, it's going to produce a magnetic field. Well, now wait a minute. This one was a magnet. This one's got a magnetic field. This magnetic field, the magnetic field created by this guy, has to be opposed by the magnetic field created by the induction of current in this coil. I know, I really need some props, don't I? Well, I'm in a closet. What do you want? Okay, so check this out. Check out this graphic. So in A, basically, my fingers here, that's the conductor, all right? And in my brush here, this is the magnet. So I'm moving in. This is the north end, right? Actually, I'll use this as the north end. So there we go. The north end is going in. Boom. All right. And because I've got a moving magnet, I get induced current. Pretty sweet. All right. Now in B, what's happening is now it's like, imagine this isn't here anymore. I mean, it's there, but just pretend. So now because I have a current passing through this coil, that will create a magnetic field. And look at the arrows on that magnetic field. Or if you like, look at where the north and the south is. Remember, this was the north on my moving magnet. And the north on the induced magnet, I'm going to call it the induced magnet, okay? Just bear with me, is opposite to the one that this one has, right? So in other words, these two magnetic fields are opposing each other. All right, so now sometime later, I'm going to pull this magnet out of the ring. And so as I pull it out of the ring, the induced current goes in the opposite direction, right? And since the current is flowing in the opposite direction, you'd apply your right-hand rule, and you can see that the north magnetic field, or the north pole rather, is in the opposite direction to the way it was before. All right, pretty wild. I've been throwing a bunch of stuff at you here. Faraday's law of induction, Lenz's law. Let's see if we can put them together. Watch this video, okay? And as you're watching the video, I want you to try and think about, okay, wait a minute, what the heck is happening here? Why is this magnet falling slowly? That's the key question. If you can understand this, you can basically understand everything you need to about this sort of stuff, okay? Lenz's law, Faraday's, you bet, okay? So just check it out. Check out the video here or here. I don't know. Check it out and come back. Wasn't that awesome? I loved especially how he at the end, you could look down the tube and see what was happening with the magnet, that it really was like, it wasn't like, you know, rubbing against the side or something. There wasn't some friction going on. This wasn't a magic trick. It was physics. It's better than magic. The idea is, as the magnet, so if this was the tube and the magnet is traveling down, there's going to be what are called eddy currents, which are basically loops of current in the copper tube, okay? So as the magnet is falling down, it creates these eddy currents, and those eddy currents create a magnetic field that's opposed to the falling magnet. So it's kind of like a built-in brake. Now, interestingly enough, this actually has a practical application in your kitchen, perhaps, right? I don't know if you have one of these. I don't, but some people have these things called induction stoves. So the idea is that, let's just pull up the graphic here. So the idea is that in your stovetop, you have this induction element, right, which is basically made up, if you look at the bottom here, you've got an electromagnet, which is basically just a coil. And as that electromagnet, it's connected up to the mains, which provide AC, alternating current, right? Which means that the current flips direction, right? It'll go one way, then the other, then the back, and does that at 60 hertz. Sorry, brain fart. Okay, so there you go. So that's the idea. So because you have this constantly flipping current, then that means that the magnetic field produced by that is going to constantly change direction. And because you have this changing magnetic field, then you're going to produce eddy currents in the pan. So in this case, we have you have to use a conductive pan. So I don't know about these. I guess most pans are conductive. Anyway, but anyway, doesn't matter. So the idea is you have to have some conductive pan, and when it's sitting on this conductive stovetop, right? The changing magnetic field is going to create these circular eddy currents in the bottom of the pan, just like we have here. Okay. Now these pans are made in such a way that there's going to be this current. It's going to encounter some resistance, just like it would if it were in some kind of a circuit. And the more resist, I don't know if you've ever touched actual resistor. If it's in a circuit, depending on what the resistance is, it heats up quite a lot. And the same thing happens here. So the idea is that we've got these eddy currents going around in the bottom of the pan, and because of the pan's resistance, it'll heat up and it'll cook your food. What's cool about this is that if you put your hand on the stovetop, right? If I put my hand on my stovetop, it's a regular stovetop. It's just a regular element. If I do that, then I'm going to get burned, right? So I don't do that. You shouldn't either. But if I put it on an induction stovetop, my hand isn't conductive, right? It's not a good conductor, right? Skin is not a good conductor. So as a consequence, I can safely put my hand on a induction stovetop, while at the same time, I could, right next door to it, have a pan or pot or whatever that's boiling away. It's pretty cool. All right, here's another application. If you ever in your life get a chance, ride a maglev train. Okay, that's my suggestion to you as someone who's probably older than you are watching this. Ride a maglev train. They've got them mostly in Asia. I'll be honest, you pretty much got to take a trip to Asia if you want to ride a maglev train. But it is something cool, right? You'll never feel quite the same. Actually, I lie. Like the maglev trains, it's almost like you're not even. It's almost you feel like you're not moving because for the most part you're not really accelerating, or at least accelerating very slowly. So you can barely feel it, especially. And yet they have this speedometer up at the top. You're typically at the front of the car, and you can see the countryside passing by, and you just know that you're going like hundreds of kilometers an hour. Right? It's bananas. Anyway, so it turns out that maglev trains actually use a lot of the same principles, this whole idea of induction. So, okay, so let me just get to the picture here. So the idea is that maglev trains actually use two sets of electromagnets. There are ones on the side of the train that basically accelerate the train or brake it when it comes into the station. Okay, so in the diagram here, those are called the lateral guidance electromagnets, and so that's basically a series of electromagnets that flip their polarity as the train moves and just basically give it kicks so that it goes faster and faster, or brakes so that it slows down. So those are the ones on the sides. Those ones aren't so super interesting. The ones on the bottom, on the other hand, these are the ones that actually levitate the train. And so this is pretty cool. The idea is that if you see this, the bottom of this train here, you've got these little bricks below the train that are called the support electromagnets. So on the bottom of the train, you've got these electromagnets that basically create the magnetic field, a constant magnetic field. And then on the bottom of the train, you basically just need to have a coil. And the coil, I mean, I'm really simplifying things because, well, I'm not a train engineer. I don't know. But the idea is that in principle, you just need to have a coil on the bottom of the train, which would then, after interacting with the magnetic field of these electromagnets, would then have a current going the opposite direction, create an opposing magnetic field, and then magnetically levitate the train. It's the exact same concept as the falling magnet in the copper tube. Just different geometry. Almost forgot. Here's your work with this lesson. Thanks for watching, and have a great week. See you, folks.